Hello and welcome back to Calculus 2. We are starting chapter 8 on techniques of integration, and the first lecture here is going to actually be the review of basic integration techniques and tricks that we learned before, which obviously includes the U sub as one of the most important and most frequent integration techniques. So we're going to start by understanding that integrals are backwards derivatives. They're also known as antiderivative. And if you start, let's say, with, let's go with x squared dx, you would integrate that into x cubed over 3, and then we'll have to put plus c. This part over here is the one that is called the antiderivative. And if this function over here is called lowercase f of x, this one is called capital F of x. So this notation, right, the same notation what we used in Calc 1. Now, if you have the definite integral, say it goes from 1 to 4, and you have your x squared dx, now you will find the antiderivative, which is x cubed over 3, and compute that from 1 to 4, where you get 4 cubed over 3 minus 1 cubed over 3 for an answer of total of 21. Obvious, right? Let's say. It's good. So you have the formula to compute. You learned this as the fundamental theorem of calculus part 1, where we said, whatever, that the integral from a to b of f of x dx is equal to the antiderivative f of x computed from a to b, and then you go f of b minus f of a. And that was the formula that calculates definite integrals to give us the value at the end. So we have indefinite integrals, those have plus c, and then we have definite integrals whose value is a number like we had 21. Now the list of 13 different integrals formulas is in the book. There is a much larger formula sheet, but we'll eventually talk about it. So now I'm going to mention few important integrals to keep in mind. Probably the most important integral of our existence is integral x to the n dx, because it's literally a multi-tool of integration here. Over n plus 1 plus c. So this particular formula takes care of 3 different types of functions, right? So your n, right, can be larger than 0 and whole number. And in that case, you have polynomial. Your n could be less than 0 and whole number. And in that case, you have rational function. And finally, n could be fraction, in which case you have radical function. So now you have these 3, and it's very simple to just say, okay, here it is, f of x to the 7 dx gives you x to the 8 over 8 plus c. So that will be the example for number 1. Then you have, let's say you have 4 divided by x to the 6 dx. You can rewrite this as 4 integral x to the negative 6 dx And when you add 1, you get 4 times x to the negative 5 over negative 5 plus c. And finally, if you have, let's say, 4th root of x to the 3 dx, that would be a radical function. You don't have to just have the square root. It could be a cube root or a 4th root or whatever root. You can rewrite it as a fraction. So it's going to be 3/4 dx, and then when you add 1, it's going to be x to the 7/4 over 7/4 plus c. So now you see all 3 examples for x to the n, and it's important to be able to work with all of them. So one formula covers 3 types of functions, right? The rest is all, e is for e, and 1 over x gives us ln, and, So other formulas are, so here, let's go with, I guess, red. The integral of e to the ax dx is e to the ax over a plus c. Integral of 1 over x dx is equal to ln of absolute x plus c. Usually you forget the absolute value and then points off and then whining later. But I just forgot half of the domain. Like, yeah, and you lost 2 out of 8. So that, wow. See, there's the justification right there. Knocking out 2 out of 10 points is only 20%, where if you forget the absolute value, you lose 50% of the domain. We just made it worse. Then we have integral of trig functions that is equal to other trig. There are 6 of them. There are 6 and plus c, all right? There are 6 of those. Integral of the constant k dx is kx plus c. That's a good one. Right. Then you have the one that I did tell you to pay attention to, dx over a squared plus x squared, or x squared plus a squared, whatever, which is 1 over a inverse tangent of x over a plus c. And I'm asking you to deal with this one because you are going to see a lot of integrals of this type in Calc 2 and Calc 3 and differential equations. So this is the one to know. I mean, all of these are to know them. It's just if you are singling out one of the inverses, that's the one.
That one pops up every now and again in the homework.
Yeah, okay. So, yeah. So now that we took a quick look at those very, very basic integrals from 4.9, it's time, and understood that they can all be definite integrals, which is 5.2. It's time to talk about the u sub, which is 5.5, and then we're going to take a look at a whole bunch of examples. So u substitution, there is a formula which is completely useless because you want to know the procedure and get very hands-on with this stuff. So if you have the integral of f prime of f prime of x times g of f of x dx is just going to give you g prime in there as well. There we go. Is going to give you g of f of x plus c. So this formula is busy and it doesn't really tell you anything until you, it does tell you, but let's just work out the example, make clear. So we have, let's say, x sine x squared dx as a problem. And this is where you really see that you are going to have to find what we call function derivative pair. And you are looking for two functions that one is the derivative of the other. So in this case, what do we have? Yes? X squared. So function is x squared and its derivative would be 2x, right? So we are immediately going to say u equals x squared and then du equals 2x dx. I don't have a 2, so I will fix that by writing the 2.5 in. So now I have 1/2 integral of sine u du. If I go here in this peanut, all right, in this peanut I have the du, and that's the du, and then you have sine of x squared, but x squared is u, so sine u. So that's how we organize and do the substitution to a place where the stuff goes. Now we integrate. We have a basic integral here of sine. So what's the integral of sine? Very, very good. And then we go, I don't care about u, I care about the x, right? Which means we put the x squared there, plus c, and there it is. I'm going to remove the peanut. Good. Another example would be integral of sine to the 6x cosine x dx. So here's more trig, right? Here's more trig, and now you are looking at this. It's a little bit different than what we had before. We still have function derivative pair. So what would be my function derivative pair now? Yes, just go. Sine and cosine, right? Sine and cosine, and you want the single one to stay for the derivative so that you can use it for du. So we are going to set u to be sine in this case, and du is going to be cosine x dx. So now the integral changes into u to the 6 du. So sine was set up to be u, and then you have u to the 6, and we're good to go. So at this point we have u to the 7 over 7 plus c, and then we have 1 over 7 sine to the 7x plus c, and then we go from there. So let's see a little bit of e action over here. How about e to the 3 square root of x divided by 4 square root of x dx? So try that one for a few seconds. So what would be u for this case?
3 root x.
Great. So u is 3 root x, and du is what?
U is going to be 1 over 6 root x.
3 has to stay in the numerator, right? So I need 3 halves. So that means I'll put 2/3 in front. And then the 4 and the 2 will cancel. So it's going to be 1 over 6 integral of e to the u du. When I use 3 halves and then 1 over root x, the 4 will come out and cancel the 2. So it was 6. Yep, we're good. So this is 1 over 6 e to the u plus c, which is 1 over 6 e to the 3 root x plus c. Now, let's say you care, right? And you want to check. Well, then you just take the derivative. Take the derivative and make sure that it worked out. So to check, all I need to do is to take the derivative. I will copy 1 over 6. The derivative of e to the f of x is e to the f of x, times the derivative of the exponent, which is 3 over 2 root x, and then the derivative of plus c is 0. So now I have 3 e to the 3 root x over 12 root x. And then when these cancel, we're going to have e to the 3 root x over 4 root x. There we go. Woohoo. Worked out great.
That way you got the 1/6.
So let me put, we need a peanut first, right? If you're allergic, take 2.
I'm not.
Then 1 only. There's the peanut. All right, so the peanut is this. Are we bueno on that? So as soon as the peanut is clear, 1 over 6 is immediately going to be clear, because you will have 2 over 12, and 2 over 12 cancels to 1 over 6. This 4 is going to jump out, multiply the 3. and you have 2 over 12, and that's 1 over 6.
Oh, okay.
Woohoo!
Where does the 4 go? I
The,
got it.
3 times 4 is 12,
Yeah, you factor it out.
and then 2 and 12 cancel to 1 over 6.
Is the derivative of root x 1 over 2 root x, or is it?
Yes. Yes.
It's positive or negative?
Positive. You can try it. X to the 1/2,
No,
right?
yeah.
X to the 1/2 would be 1/2. You drop down exponent, right? And then
1/2.
and then plus 1. And then plus 1. I can do it this way. And then plus 1. So 1/2 x to the negative 1.
Yeah.
And that's the negative 1/2 that pushes it down in denominator. But the initial 1/2 is positive. Cool. All right. Let's take a look at some of the integrals that you are going to be sick of very soon. Integral of 6 divided by x minus 9 dx. You will be skipping 100% of the work for these types of integrals in like 2 weeks. So, this problem, I mean. Right now, you might go and do all of the steps. Yeah, this classroom is freakishly cold, so they have all of these space heaters. You have to plug it in. Yeah.
You're both in trash.
Yes, that's good.
It's a personal game. It's not a regular. There's an alarm.
Very pleasant. So you get a better alarm. It's still yeah. I start every day in the state panic.
I was wondering why I was getting completely different answers for the last problem. I wrote it down as e to the cube root x over 4th root x.
Okay. 3 times squared. Okay. Now that yes.
Way off.
Okay. All right, guys. So you are going to see this type of the integral at least 117 times in Calc 2, and then it's going to keep popping up later on. What you need to see here is that this is of the form integral 1 over x dx, right? Which leads into ln. So the way we do this problem is we first kick the 6 outside. We have, you can also call it dx over x minus 9 if you want to. And we create our u as x minus 9, and the du is just dx. So the whole integral collapses down to 6 integral of du over u, which is 6 ln of u, and you put the absolute value. They're not optional. You have to put absolute value there, otherwise doom with 7 O's, not 2. That's for noobs. 7-0 doom. And then you have 6 ln absolute x minus 9 plus c.
I got it right.
So, it's so weird to do it with the left, but I have to. So you will quickly, as soon as we go through partial fraction decomposition, which I believe is 8.5, I believe, when you see something like this, you will say, oh, that goes in front of ln, that goes inside the ln, as soon as you see the problem, right? Right now, sure, you do your u sub, and it's all nice. But just imagine that every single problem you do in 8.5 in class and for homework and for exams will end with these pieces and inverse tangent pieces and, you know, some other pieces. So, but, you know, I would say about 70% of the pieces would be this, and then maybe another 20% would be inverse tangent, and 10% everything else. So you will be sick of this type of an integral. So you might as well start this. It is going to pop up a lot. Cool. So now let's see what else we can. Oh, let's not forget the doom and gloom. How about if you have x squared plus 3x minus 6 divided by x plus 2 dx? Hardly. Great. You could just notify me that I'm live. I have no clue. So can we do u sub on this one? Obviously not, right? What do? Give up. Exactly. Let's go have lunch.
Why can't we use u sub? I was just starting to do it. I was getting there.
We can't use because of the 3. This 3 is what? Yes.
It's a long divide.
Yes.
Yeah.
Long division.
Long division of polynomials. And this is the good time to write the rule in blood on the side. This over here is called rational function, and it's of the form p of x divided by q of x where both of these are polynomials. So this is, we are getting into what you want to call the trick, or you know. So P of x divided by Q of x, and what I'm going to say here is that when exponent of P of x is bigger or equal Q of x, we need to divide. So that's the way to solve these problems. So if the exponents are the same, or the top is bigger, like in this case, the first step is long division. And then whatever else has to happen in life after that. So now I'm going to start with x plus 2 divide into x squared plus 3x minus 6. So that's where I start. And then x goes into x squared x times x is x squared plus 2x when you multiply back. Then you subtract it. These guys cancel. You have x minus 6. X goes into x plus 1 time. 1 times x plus 2 is x plus 2. Then you subtract it. These guys cancel. Negative 6 minus 2 is negative 8, which means that the remainder is negative 8 over x plus 2. So this integral is x plus 1 minus 8 over x plus 2 dx. And since you have addition and subtraction, this is going to be this guy is the ln guy, right? So I'm just going to say ln from the previous problem. So we just write the answer. We immediately know what the answer is. What's the integral of x? Beautiful. What's the integral of 1? So plus x. And then minus 8 ln x plus 2 in absolute values.
I'm definitely going to forget those absolute values. Just go ahead and cancel my
Just cancel your points. That's it. It's just go ahead. Take them over right now.
handicap, and then we just won't have to worry.
Yes.
Oh, okay. No, I got it. Hold on.
So the this ln looks like in from it's ln. So let me curve it.
I don't think I've ever done that. That's how I write it, because I confuse myself.
No, I need the long division of polynomials. I don't think I've ever done that.
Yeah, so like if
Long
we,
division of polynomials? Yeah, it's intermediate algebra.
well, I remember doing it,
Completely
yeah.
honest, completely honest. Like I didn't have algebra here, and last semester is the first math class I've taken in about 8 years.
So it's going to be YouTube. Type in long division of polynomials in YouTube. You should have about 500,000 kids and videos. It's going to take. Don't try to work them all.
Well, no, I'll just do like compound.
You just gotta practice like 1 or 2.
It's really simple. If I can get it, I'm
no,
sure you'll
this
be
makes
fine.
sense.
If you know how to divide numbers by hand, then long division is just the one upgrade. Now that's even longer.
It's
I was teaching in a classroom of 8th graders as part of the teaching training, and I was doing long division in front of them because they don't know how to just cancel stuff out, and I forgot how to do long division because it's been so long. And if you've ever done embarrassment before, forgetting long division in front of 38th graders.
Oh my
Pretty
God,
good.
they're still young and still answers too.
How about forgetting a speech in front of 25,000 people? I mean, forgetting the paper. 25,000 people, that was my first time.
Oh my
Oh.
God.
You forgot the
Wait, I have a question.
Oh, was that the
Well, I knew the
Pascal's,
speech, so.
the Pascal's triangle? When you were
No, that was back in Serbia before we hit for the final protest. So I was
picture?
Hmm?
You said you were going to bring a picture.
Because I have to scan it. Actually, I can because I have to scan all the pictures. They're doing the exhibit of memorabilia, photos, news articles, and all about 20 years of movement. To celebrate 20 years of the movement. It's on the 3rd, October 3rd, because the protest is October 5th, so it's going to be open for October 5th as well. So my mom collected a whole bunch of stuff that she found throughout the house, gave it to these guys to do the expo. And they contacted me to find all the photos that I have. So I'll be scanning those photos in and just remember.
You could put the photo on the board. I remember you used to put like hats on the board during the exam. Put that photo on.
You want to see me with the rider shoe?
It would be very,
It's going to be
motivating.
so great for you guys to.
I'm battling my exam.
Huh?
I'll be battling my exam now.
Yes.
Basically the same thing.
Please.
All right, so let's see more of these.
I have a question.
Yes.
So if we see that like we can't factor it, like something like that where it's the polynomials in both the numerator and denominator and we can't factor it, then we know to do long division? And just do it
Yes,
that way?
if you cannot factor and cancel, yes, it's a long division. If you can factor and cancel, then that's hack. Because if you look, long division works 100% of the time. Even if you don't see the factoring, when you long divide, it will divide evenly without remainder, and what stays would be what you would have once canceled.
Oh.
So yeah, it's that cool.
It seems like it's easier to integrate after you do this than if you were to try to factor it out and do it. If you're good at the long division, because here you're left with just everything without a denominator, and your last one's always going to be an ln if there's a remainder.
Yeah, 100% of the time. Yep. And then you go to the homework and you go. I've seen a meme 3 or 4 days ago. Let me just refresh. What did the meme say? It says, why I hated math. In class, 5 plus 5 equals 10. For homework, 734 plus 555 minus 432 divided, right, equals to blah, blah. Test. With 2 sheep flying, one yellow and the other one headed right, how much does a pound of asphalt cost given the cow is 10 years old? Like, yeah.
God, that's literally how I feel all the time.
I know. All right. We haven't done any definite integrals, so how about 0 to 2? Something simple, go quick. X over x squared plus 4x plus 8 dx. This is one of the evil ones as well, but hopefully it will. It's going to be another one of those YouTube things. Let's waste another afternoon. I'm not going to let you bake on this one for too long because it's not using anything we used yet. Does anyone know?
Can't you separate it like x over
Nope.
x? No? Damn it.
You can only separate if addition and subtraction is in the numerator, right? Fractions can be separated if it's in numerator. If it's in denominator, it's like 1 unit. No, because of the 8. 8 doesn't have an x, so you can't factor out x because of that 8. Yes?
It's not u sub?
It's not a u sub because the u sub over here would be 2x plus 4, so you need x plus 2 on top. Now, that might be a way to hack into a problem that way. I didn't try it. If you do plus 2 minus 2, and then you still have negative 2 over this to deal with later. So there might be a way there. There might be a way. But it's not the immediate way to solve this problem.
Can you like flip the integral?
Nope. That would be a reciprocal. Nope. You need two-sided, you need the equation. You flip the left side, you flip the right side.
You can't like flip it and then flip it back after?
Nope. Ready? And completing the square. From
Oh my god.
complete the square, another one from the ancient algebra, where you look at ax squared, no, not ax squared, sorry, x squared plus bx plus c, and you use b over 2 squared to work out the problem. So we have x squared plus 4x plus 8. So your b is 4 over 2 squared, which would be 4. So you can split the 8 into 4 plus 4, and then use the first 3 to complete the square. Square root of the first, sine of the second, square root of the third, and you still have the plus 4 left. So now we put that in the problem. So completing the square procedure was the one we used to get here. And it's, again, as I said, another one of those YouTube things where you say, I got nothing to do next hour, so let's go. Complete the square. Okay. So now what? Well, we do have x plus 2 squared, so hopefully we can use the u sub on x plus 2, and du is dx, right? So let's go and use this. Well, the denominator is u squared plus 4, dx is du. What am I going to do for x? Yes?
Is it back sub?
Back sub, nice. Back substitution, very good. So x is equal to u minus 2. U minus 2, back substitution. Excellent.
Oh my god, wait, what is that?
Because we don't have anything to we don't have anything to replace that x on in the numerator. So we had to solve our substitution for x. It was called back substitution. I did talk about it in 5.5 last semester, but there are only like 1 or 2 problems.
Oh wait, basically you're just setting the x equal to
u minus 2. Yep. It's called the back substitution because you are bringing x back in terms of u.
Okay.
And now we need to switch our limits. So u1 is going to be, old limit was a 0, so 0 plus 2 equals to 2. And u2, the top one, is going to be 2 plus 2, which is 4. So that's a 4. So now the entire integral moved into a u domain, and we don't have to worry about x, and we don't have to go back to x either, because we have the u limits and we have this. We are not done, because we have now u squared plus 4, and this is where we u squared plus 4, that one doesn't factor, right? It factors over complex numbers. U squared minus 4 factors. U squared plus 4 factors over complex values, so we can't factor and cancel. This is where we get to split. Yeah, we get to split now, because we have 2 terms in the numerator in a fraction, so this is what splits into 2 integrals. So 2 for u over u squared plus 4 du plus integral of 2 to 4, actually minus 2 over u squared plus 4. Actually, we can kick this 2 outside. How about that? So now, since we have the x minus 2, u minus 2, we split into u minus 2 separate fractions with a common denominator of u squared plus 4, and each one of them gets their own integral with their own 2 to 4 integration. And all we need to do is to solve each one of these individually, and we're done. So what should we do on the left? Nope, because of plus 4. Yeah, it's going to be u substitution, but let's call it a g substitution or something else. You have another letter that is favorite letter?
Isn't that the inverse tangent?
Which one?
On the left, u over u squared plus 4.
No. It's the one on the right that is inverse tangent. Inverse tangent has a number on top. And this is perfect one to see the difference between the ln and inverse tangent. Because we can use now, let's go orange. Over here, g equals u squared plus 4. dg is equal to 2u du. So I need a 2 and a 1/2. And this puppy over here is going to be tangent inverse, because it's in that form.
So it won't be equal to doing ln and then doing the inverse chain rule? Like if you do...
What do you mean?
You do like if negative 2 ln u squared plus 4 over 2.
No. We have to do the inverse tangent on that one. You got your 1/2 on this side. So we have 1/2 integral of, and now this is going to be dg over g minus 2. And then we have inverse tangent, so it's going to be 1/2 inverse tangent of u over 2. It's going to be calculated from 2 to 4 eventually. And dg over here, it's 1/2 ln of u with the of g, sorry, one limit g, and the limits are, when you plug in 2, you get 8 on the bottom, because 2 squared is 4, 4 plus 4, and then 4 squared is 16 to 20. These guys cancel, minus tangent, put the squared, holy nightmare. Inverse, there we go, of u divided by 2, 2 to 4. So 1/2 ln 20 minus ln 8 minus tangent inverse of 2 plus tangent inverse of 1. Because 2 divided by 2 is 1, minus is plus, excellent. So now the boss move is to write this as 20 over 8. So 1/2 ln 20 over 8, because you can combine ln's into a division of arguments there, minus tangent inverse of 2 plus, and this is pi over 4, because it's inverse tangent of 1, it's 45 degrees. 20 over 8 cancels by 4, so we have finally 1/2 ln 5/2 minus tangent inverse of 2 plus pi over 4. This is a good integral when someone tells you, what do you know? There you go. This is an awesome problem. Also can be used for Thanksgiving.
I was just going to ask.
I have a question about the inverse tan
Yes.
thing. So I know it's supposed to be like 1 over a squared plus x squared. So what matters is that 1 is a variable and 1 is an integer. It doesn't matter which order they're in.
Yes, because it's addition.
It's always going to be the variable over the integer.
Not variable over the integer. Integer, it's the number divided by variable plus integer. Or
well, I mean, like after you do the integral, like you have u over 2 there, but the way it was in the problem, it was u squared plus 4.
Oh, you have to chase where your a is.
So it's the a is always the integer and the other is always the variable.
Yeah.
So it'll always be the variable over the integer after you integrate.
Yes.
Okay.
The square of the number.
Okay.
So we have to complete the square when the denominator has a greater exponent than the numerator.
That's one of the possibilities. If the basic u sub doesn't work right off the bat, then
Scroll up a little bit.
Scroll up a little bit, there you go. So
I can see the line. Maybe one more square.
scroll up a little bit. It's always going to be 1/16 of an inch. No, the cool thing about the live stream is when you are in class, you can watch on the computers in your desk the stream, and you can go and slide back anywhere you want, because the live stream allows you to go back all the way to the front of the stream, and then you can just put the slider all the way back and go forward.
Past the present.
Oh yes, to see the future. That's what you like, right? All right, well guys, that's it. I hope you're not disappointed. That was the review of integration, mainly u sub, as you can see, and most of our chapter 8 is going to be problems dealing with things with various algebra and manipulation techniques, so that we can get to u sub and finish off the problem. I would just make one more petition, should I say, to change your limits every time when you have the definite integral and you have to use u sub. Change your limits into u. Don't go back. unwrapping it, because as you can see, this problem went from x to u to g, and I changed the limits from 0 to 2 to 2 to 4 to 8 to 20. Because once you are in g, if you didn't change the limits, you have to go from g back into u, from u back into x, so that you can use your 0 and 2 all the way up in front. A little bit too much, right? So if you keep changing the limits, and to change limits, it's very simple, because all you do is you take your equation, that is substitution equation, and you stick these numbers one at a time. So g, I put 2, 2 squared is 4, 4 plus 4 is 8. Stick in 4, 4 squared is 16, plus 2 is 20. And I get my dg limits, which I didn't write here, I don't know why, as 8 over 8 and 20. And you, as simple as that. Take the 2, stick it in here. There was a lower limit. 2 squared is 4. 4 plus 4 is 8. Stick it in a lower limit. And now you don't have to go back to the old variable, because the new variable is in terms of g, and the limit is in terms of g, because look, g equals, you stick this number in, right, and you get g equals 8. So now limit is g, integral is g, and you don't have to go back, right? This is why definite integrals are better than the, if we were to do this in original, right, in indefinite, thank you very much. I need to drink some bleach. If this was the indefinite integral, you have to go back to u, then you have to go back to x, and then plus c at the end, and it's just a lot of, backtracking. Trig substitution is coming, where, we're going to deal with also the values of trig, not just the numbers, in which case, right, try to avoid as much as possible. If you have definite integrals, this unwrapping back to the original stuff. Just change the variable and keep going. Okay?
That's just what you answered my question. I was just going to ask about, so with indefinites, you have to unravel it to stay in new, but
for indefinites, you have to, yes. And for the definite, it's much faster if you switch the limits and just keep going, because you don't have to worry about where was my substitution, because now you have to go hunt down what the g is equal to plug in, and then, but it's u, still not x. Then go find where u was, right? And especially if you have, a little bit irradical way of writing things, it's not going to be bueno. So let's take a break. When we come back, 8.2 integration by parts.